Welcome to the course on nanostructured materials, synthesis, properties, self assembly and applications. We are going to start the first lecture of module 3. We earlier had module 1 comprising 2 lectures and module 2 comprising 12 lectures. So, totally we have completed 14 lectures, and today will be our 15th lecture for the whole course, and this is the first lecture of module 3. And the first lecture we will start with fullerenes and carbon nanotubes, and we will have 3 lectures on fullerenes and carbon based nanotubes. Today we have the first lecture of this. Now, fullerenes, as some of you must have heard, was discovered in 1985, but previous to 1985 also there were reports about it. So, we will discuss the historical development of this structure, nanostructure called fullerene. You must have all known that normally carbon has 3 allotropic forms. One is diamond, the other is graphite, and we have amorphous type of or non crystalline carbon. Today we know of many other forms of carbon, and among them the first to be discovered among these new forms of carbon is the C60 molecule, which is also called the buckyball and is also called fullerene. Today there are many other carbon based molecules which are related to this buckyball with large number of carbon atoms per molecule, and there are more than 30 forms of such fullerenes. Now, why this is called fullerene, we will come to that. It basically looks like a soccer ball which has got 6 membered carbon rings and also 5 membered carbon rings. So, this typical molecule has 60 carbon atoms, which is arranged like in a soccer ball or a football as we know in India, and if you replace the vertices of each of those with carbon, then this becomes a C60 molecule, and this was discovered in 1985 and a Nobel Prize was given for this discovery. So, historically was this discovery of C60 in 1985 the first time people thought of this molecule? No, people have thought about such molecules much earlier. For example, it was predicted by Osawa in 1970 that there can be a molecule like C60. In 1970, there was another proposal of a model of C60, but the experimental evidence was not very strong, and hence this structure was not accepted at that time. These results have been later acknowledged, for example, in the journal Carbon in 1999, much later, that Henson proposed this structure in 1970. Today we know that it is correct and it is known experimentally. Apart from that, in 1973 in USSR, earlier USSR, it was calculated using quantum chemical calculations that a molecule like C60 would be stable, and the electronic structure of the molecule was calculated. The energy levels of the molecule, the molecular orbital was calculated for a molecule like C60 theoretically, and a paper was published in proceedings of the USSR Academy of Sciences. So, there were several such studies which were kind of indicating that there can be a molecule like C60, a very symmetrical molecule, a molecule which looks like a football or a soccer ball, and this molecule was predicted theoretically, and some experiments was done, but not clinching evidence was not there. But in 1985, a team of people from England and USA contributed to the actual discovery of C60. The main players in the discovery of C60 were Harold Kroto, Robert Curl and Richard Smalley, and James Heath was a student at that time, and these 4 people worked in Rice University, though Harold Kroto, who was visiting Rice University from UK, and together they discovered C60 in 1985. And the idea behind their discovery was they were looking for molecules and which can be synthesized in the upper atmosphere or in space, where plasma exists, and they were trying to create a plasma or through an electric discharge, where such molecules which are probably formed in outer space can be recreated in the laboratory. During that arc discharge of using graphite electrodes, they found a black colored material getting deposited, and then it was analyzed using several techniques including NMR or nuclear magnetic resonance, and they confirmed that it is a C60 molecule, a molecule which has 60 atoms of carbon, and the structure was just like the structure we showed, like a soccer ball. So, this was the discovery of C60 by Kroto, Curl, Smalley and their co-workers at Rice University using electric discharge, and then analyzed by several techniques, gave the structure which was exactly like a soccer ball with 60 carbons having hexagonal rings and pentagonal rings. Later, such C60 or fullerene kind of materials have been found naturally occurring in Russia, and it has also been discovered in cosmic dust in a distant star several light years, several thousand light years away. So, C60 molecules are present in space. They are also found in minerals, and of course, it was made in the laboratory. And for their work, Harold Kroto, Robert Curl and Richard Smalley were awarded the 1996 Nobel Prize in Chemistry, though the discovery they made was in 1985. They were awarded the Nobel Prize in Chemistry in 1996. It was a great discovery. A new allotrope of carbon was discovered, and it brought about several new molecules related to C60 like C70, C80, C82 and several large cage like structures, ring with cluster like structures were discovered after these fullerene or C60 was discovered. So, the type of fullerenes that we know today are like the common C60 molecule we just discussed. Apart from that, we have now made several nanotubes which are made up of carbon. These hollow tubes, which have very small dimensions, can have single walls or multiple walls based on carbon. These nanotubes are very important for several applications, as we will discuss in the coming lectures. Then you can have mega tubes, much larger in diameter than the nanotubes, and can be prepared with walls which have varying thicknesses. Then you can have fullerene rings. You can also have fullerenes which are linked by carbon chains. So, those are called ball and chain kind of dimers. So, two buckyballs or two C60 molecules which are linked by carbon chain will then be called a ball and chain dimer. You can have two buckyballs which are connected to each other to form fullerene rings. Then you can have what are called nano onions, spherical particles based on multiple carbon layers surrounding a buckyball core. So, you have a C60 core and there are layers of carbon surrounding that C60 molecule. So, you may have 5, 6, 7 layers of carbon which is surrounding a C60 molecule. So, if you take out one layer, another layer will be there. So, that is why the structure will be like an onion, and hence it is called nano onion, because the dimension of the C60 molecule is nanometer in size, less than 1 nanometer, it is around 0.7 nanometers. Now, the name fullerene comes from the name of an architect, Buckminster Fuller, who first made domes which are like the fullerene structure. So, these geodesic domes, as they are called, have been made in several places in Canada and many other places, which have domes which are in the shape of this kind of hexagonal rings and pentagonal rings fused together, and if you take half of it, then it forms a dome which is very similar to domes which Buckminster Fuller, an architect, made in the 1970s in several countries. And so, this molecule is called fullerene after the name of Buckminster Fuller. So, fullerenes have 3-dimensional network of carbon atoms. They contain pentagonal and hexagonal rings in which no two pentagons share an edge. So, hexagons can share an edge, one hexagon can share an edge with one pentagon, but two pentagons cannot share an edge. Then each atom is connected to exactly 3 neighbors, 3 other carbon atoms, and each atom is bonded to 2 single bonds and 1 double bond, example in C82. So, again going through the main characteristics of C60 molecule, there are 60 carbon atoms, there are 5 membered rings, and there are. So, this is a 5 membered ring, as you see here, there are 5 carbons and there are 6 membered rings here, and this 6 membered ring can be connected to another 6 membered ring in this C60 molecule, but 2 5 membered rings cannot be connected to each other. The van der Waals diameter, that means the distance between the electron clouds from one end to another end, is about 1.1 nanometers. Okay. So, that is like 11 angstrom, but if you take the nucleus of the carbon here and the nucleus of the carbon, then that distance is around 0.7 nanometers, which is much less than 1 nanometer. So, it is on an average you can just say that the fullerene molecule is of the order of 1 nanometer, but of course, it depends on what kind of diameter are you defining. If you take the van der Waals diameter, it is 1.1 nanometer, and if you talk about the nucleus to nucleus diameter, then it is 0.71 nanometer, which is equal to 7 angstroms, 7.1 angstroms. Then you can have, other than C60 which has 60 carbon atoms, you can have C70 which has 70 carbon atoms. You can have C72, C76, C84. So, you can have fullerenes with different number of carbon atoms, but the shape will change slightly. Now, your number of hexagons and number of pentagons will change, okay, because the number of hexagons and the pentagons are related. Always you will have 12 pentagons, the hexagons will change and that number will be equal to V by 2 minus 10, where V is the number of vertices. So, this is given by Euler's polyhedron formula. So, if you have C82, if you have 82 vertices, then you need to know how many edges are there and how many faces are there, and you can use this formula V minus E plus F equal to 2, where V, E, F are the vertices, edges and faces, and you can find out that there will be exactly 12 pentagons and V by 2 minus 10 hexagons. So, if you have C84, if you have 12 pentagons, right, then if you the number of vertices is 84. So, 84 by 2 is 42, and 42 minus 10 is 32 hexagons. So, you can say that C84, that means the cluster or the molecule C84 will have 32 hexagons and 12 pentagons. So, in all these fullerenes you will have variable number of hexagons and you will have 12 pentagons, and the number of hexagons you can find out if you know the number of vertices, and the number of vertices you can get from the number of carbon atoms you have on this cluster. So, you can have a large variety of these fullerenes, all related through hexagons and pentagons of carbon. Now, recently in 2007, instead of carbon, boron have at the vertices has also been created to lead to a buckyball kind of structure. However, the formula which has been obtained is B80, and with each boron forming 5 or 6 bonds, and it is predicted that it will be more stable than C60. So, this kind of boron buckyball has not been isolated, it has been predicted like theoretically and described, and it is suggested that if it is made, then this V80 molecule will be more stable than C60. So, there are a lot of new things related to fullerenes which are still under research. How do you synthesize these fullerenes, these C60, C70, etc.? So, the technique which is used is either you take a graphite is basically carbon, one allotrope of carbon, which has got sheet like structure or layers of carbon forming hexagonal rings, and each layer separated from another layer by van der Waals distances of around 3.3 angstrom, and this graphite, if you evaporate by shining laser, then you can get some soot, some carbon material deposited from where you can extract fullerenes. Another method is what is called the arc discharge method. This is a method where you use 2 graphite electrodes. So, again graphite is being used, but you have 2 graphite electrodes. So, you know, in the electrodes you apply a potential and you generate a discharge between the 2 electrodes. So, there is a small gap between the 2 electrodes, and between that arc has to be formed. So, when you apply a very high potential on the 2 electrodes, then and an arc is created, then some soot is deposited in the chamber around these electrodes, and this technique was developed in 1990 by Krashmer and Huffman, and this also leads to several fullerenes. So, you can use the technique of shining laser on graphite and collecting the soot, or you can use a arc discharge method to using graphite electrodes, by which you can generate soot which collects on the inner walls of the chamber, and which you can collect, and from that you will get a variety of C 60, 70 type of fullerenes, and then you have to separate them. Then you can use other techniques like where electron beam evaporation, where you can produce the higher fullerenes to a larger amount, or you can take some aromatic compounds and then heat them. So, you take aromatic compounds like normally heat them and you can get a soot. From that soot also you can get some fullerene type of compounds. Of course, the proportion of which fullerene you get depends on the method, and to get pure fullerenes by one method is quite a tough job. Normally, you have to separate these fullerenes once you get the soot through different chemical processes. Now, what would fit inside a buckyball or a C60 molecule? So, you see this is a C60 molecule, and if can we put something inside that, that has to be smaller in size than this diameter of around 1 nanometer or 0.7 to 1 nanometer, depending on how you define the radius, the distances. So, either you take the van der Waals distances or you take the distance between the nucleus to the nucleus at the end of these diameter. So, what would fit inside a buckyball? Of course, it has to be much smaller than 7 angstrom or much smaller than 0.7 nanometers, and such materials where there is something inside the cage are called endohedral compounds. These are also called cage compounds or endohedral compounds. So, nitrogen, can you put an atom of nitrogen? Sure, you can put an atom of nitrogen, because what is the diameter of the nitrogen atom? It is of the order of 1.2 angstrom or 0.12 nanometers, which is much smaller than 0.7 nanometers is the diameter of the fullerene. So, definitely you can put nitrogen. Can you put hydrogen? Hydrogen also we can put, because it is of the order of 1.5 angstroms or 0.15 nanometers. So, we can put a molecule of hydrogen in this cage. Now, can we put a larger molecule, say a molecule of sulfuric acid? So, molecule of sulfuric acid has a diameter of approximately 7 angstroms, which is like 0.7 nanometers, and you know this whole thing is of the order of 0.71 nanometers. So, this will be very difficult or more or less impossible to put a molecule of sulfuric acid inside a C60 cage. So, not likely. So, this is not likely to be the case. Now, such molecules, like if you put nitrogen inside this C60 molecule, then these are called endohedral compounds, and these endohedral compounds are given by this formula, where M is whatever you have put inside the cage. So, if it is nitrogen, then you write N at C60, that means N is inside C60. If you put lanthanum, a rare earth element, and it is known that it goes inside this cage, but lanthanum goes in to a larger fullerene C82, which has a larger diameter than C60, and lanthanum is a bigger atom than nitrogen, and so lanthanum goes in a C82 kind of a fullerene, but not a C60 fullerene, whereas a small atom like nitrogen can go inside C60. So, both of them are endohedral fullerenes, because they are lying inside the cage, and the formula is M at C60, where M is inside the cage. Now, can we have exohedral? This one was endohedral, means inside. Can we have exohedral? Yes, we can have. So, this is the C60 molecule, and you have got molecule on top of it outside. So, this is called an exohedral compound. So, we can have endohedral compound and we can have exohedral compound. In the exohedral compound, you can have either inorganic groups. So, you may have a metal with some ligand. So, you can have say platinum or some nickel or gold, some metal with some accompanying ligands on the surface of the C60 or C70 molecule, and this is another projection. So, the C60 or C70 molecule is inside, and you have got these atoms outside. So, this kind of exohedral compounds have also been made in the laboratory. and these give you lot of applications, because you can modify the properties of C60, C70 using these molecules which are attached outside on the periphery of the surface of C60 or C70 or other fullerene type of compounds. Now, you can also have atoms bound to fullerenes as salts. For example, you can have a salt where you have a positive metal and a negative anionic C60. So, when you have an anionic C60, then it is called a fulleride. So, if it is neutral, say 660 molecule, then we call it a fullerene. When you have a anionic C60, then we call it a fulleride. So, this metal cation is like a typical cation that you study in chemistry. Cations are formed from elements which donate electrons easily. So, you have these alkali metals, alkaline earth metals like lithium, sodium, potassium are alkali metals, and you have elements like calcium, barium, strontium which are alkaline earth materials. They like to donate electrons, these elements. So, when they donate electrons, the electrons go to the C60, and C60 can accept those electrons, because there are a lot of orbitals in C60, pi orbitals, and you can transfer electrons, and then C60 becomes negatively charged. So, depending on how many electrons you donate, this charge will change from 1 minus, 2 minus to n minus. So, you have a cation which is outside, and you have x the number to balance the charge over here. Okay. Now, what happens when you add these electrons? When you add these electrons, then the electrical conductivity or the resistivity changes, because now you are adding electrons to this fullerene moiety, which becomes a fulleride, and the electrical resistivity decreases by several orders of magnitude in the case when you are adding alkali metal ions. As x increases, you reach a minimum in the metallic resistivity for x equal to 3. So, the typical formula that you can generate in these fullerides are something like M3C60, that means 3 moles of potassium or rubidium or cesium per 1 mole of C60, that is the maximum it goes. So, in that case you will have 3 electrons transferred to C60. So, the charge here will become 3 minus, and actually several of these materials like K3C60 or rubidium 3C60 become superconducting at low temperature. So, at 30 Kelvin, which is minus 243 degrees Celsius, for the metal being rubidium, which is a alkali metal down the group, this compound rubidium 3C60 becomes a superconductor at low temperatures of 30 Kelvin, which is minus 243 degrees centigrade, and has the superconducting properties, which means 0 resistance, perfect diamagnetism, and will show levitation and other properties that any superconductor shows. So, in C60 and fullerene kind of materials also you can see superconductivity. Now, you can also recently it has been shown that an organic compound like CHBr3, it is like bromoform, it is called bromoform, like you have chloroform for CaCl3, you have bromoform, and this can be added to C60 to increase the conductivity or lower the resistivity. So, if you have metal ions like potassium, rubidium, etc., also you can lower the resistivity by transferring electrons. Similarly, it has been recently shown that organic compounds can also be added to C60 to show increase in conductivity or decrease in resistivity. Now, both combination of endo and exohedral compounds, that means, you have gadolinium GD, it is a lanthanide, that means, it belongs to the lanthanide series, and gadolinium is inside the C82 moiety. So, this is the formula for an endohedral compound. So, gadolinium is inside the cage of C82, and outside C82 you have got hydroxyl groups. So, this is the exohedral part and this is the endohedral part. So, you can have a combination of endo and exohedral compounds, and this is a classic case. So, this is what I just mentioned, the gadolinium is inside the cage and the outside is covered with hydroxyl groups, and it is possible material, very good material for magnetic resonance imaging. That is what their research has shown, and there is lot of potential in this material. It has also been shown that this material can be used for anti-cancer therapy, which is very important, and this kind of material based on gadolinium can be made as a endohedral compound and can also be made as a endo and exohedral compound. Now, there are several other properties of fullerenes. Now, fullerenes, if you apply pressure, so you apply pressure from outside, external pressure, very high pressure like 3000 atmospheres. So, we are at 1 atmosphere. Now, imagine 3000 times that pressure is falling on an object. So, very high pressure, the fullerenes get deformed, but as soon as you remove the pressure, the fullerenes get back to their original shape. So, this is a very interesting property of fullerene, that after being subjected to very high pressure like 3000 atmospheres, if you release the pressure, the fullerene molecule again comes back to its normal or original shape. Then the fullerenes do not bond to each other through chemical bonding. So, if you take two fullerenes, they bond to each other through weak van der Waals forces, and like in graphite, where you have got layers of rings of carbon atoms which do not bond to each other through covalent bonds, but through van der Waals bonds, and hence graphite is a good lubricant. Similarly, fullerenes also do not bond through covalent bonds to each other, and hence they are also used as good lubricants. There are catalytic properties of fullerenes which has been shown. For example, a very important reaction industrial process, which is one of the 10 most important industrial processes in the world, is to convert ethyl benzene to styrene, and C60 has been shown, the fullerenes have been shown to be good catalysts in this conversion of ethyl benzene into styrene. There are other properties like electrical conductivity, data which can be used in data storage devices, in solar cells and in fuel cells. These fullerenes also show large nonlinear optical response. So, nonlinear optical response means that if you have a frequency omega, then you can generate a frequency 2 omega or 3 omega. That is nonlinear kind of behavior is observed when you use fullerene type of materials, and this is important for telecommunications. Now, there have been many applications as drugs and also as vesicles for drug delivery. So, C60 or other fullerenes have, or their derivatives have been used as drugs, and the C60 has been used to make vesicles, that means channels through which drugs can be delivered inside the body. So, there are lots of properties of fullerenes. These are some commercial and biological applications like sunscreens, which is due to the photophysical properties of fullerenes. They are used as antibacterials due to their chemical reactivity and redox properties and superconducting properties, like in the alkali metal doped fullereides like K3C60 or rubidium 3C60, which shows superconducting properties. So, you can have photophysical properties, antibacterials and superconducting properties in these fullerenes or the derivatives of fullerenes and fullereides. Now, in fullerenes or their larger congeners like C82 etcetera, you had a kind of a spherical molecule like a spherical cluster, but if we go towards a cylindrical object, then we get what are called carbon nanotubes. So, a cylindrical fullerene was discovered in 1991 or was exactly understood in 1991 by Ijima in electron microscopic studies, and this nanostructure has diameter in the nanometer range like 1 nanometer or so, but the lengths can be very large, they can be 100 nanometers or they can even be much longer. So, the internal diameter can be varied from 1 to 15 nanometers and length can be much larger up till several microns. So, several thousands of nanometers you can extend, and these carbon nanotubes, also called CNTs, have tremendous applications. They can be made of a single layer of graphene sheet, that means only one layer of carbon is present and rolled together to form to a tube, or there are multiple layers. So, if it is made up of only one layer, then it is called single walled nanotube. If it is made up of multiple layers, then it is called multi walled nanotube. So, as you see here, there are 1, 2, 3 and 4 layers. So, this is a 4 layer multi walled nanotube, of course, all made of carbon, but you can also make single wall nanotube, double wall nanotube etcetera. They have lots and lots of properties, very interesting properties. Many of these are semiconducting in nature, but you can also make conducting nanotubes. So, typical room temperature resistivity is given here, it is around 108 ohm centimeter, it should be ohm centimeter, which is the resistivity of simple carbon nanotubes at room temperature. Now, these carbon nanotubes are made of 1 atom thick sheet of carbon. So, if you take graphite which has got layers of carbon, hexagonally oriented carbon. So, you have got rings of carbon, and if you have one layer of carbon only, then it is called graphene. But if you have several layers of carbon, one below the other, which are connected through weak van der Waals forces, then that is graphite. So, graphene is only one layer of graphite. Now, if you take that one layer of graphite, which is called graphene, and you roll it up in a cylinder, then you get the carbon nanotube, and if you have only one layer, then you get single walled carbon nanotube, and if you have several layers, you will have multi walled carbon nanotube. Now, these sheets, if you are rolling the graphene sheet, this how are you rolling the graphene sheet will change the nature of the tube which you will get ultimately. So, the sheets which are rolled at specific and discrete angles will give rise to different types of nanotubes. Some of them will be chiral, the others will be called zigzag or armchair, as we will discuss. So, you can get single wall nanotubes, multi wall nanotubes, chiral nanotubes and several other kind of nanotubes, and individual nanotubes align themselves and are weakly held by van der Waals forces. So, if you have several nanotubes, then you get a bundle of nanotubes, and these nanotubes interact with each other through van der Waals forces, and they kind of form ropes in one direction. Now, the chemical bonding of nanotubes inside the carbons are all sp2 hybridized carbons. So, that is true for all these carbons in these nanotubes. So, to have a look at these nanotubes, this is a single wall nanotubes, and this diameter is of the order of 1 nanometer, and this is a multi wall nanotube. So, you have one nanotube here, and then this is the second nanotube, and then you have a third nanotube. So, this is a multi wall nanotube. It was observed first by Endo in 1975, but was really highlighted by Ijima in 1991, and the world came to know about carbon nanotubes through Ijima's work in 1991. Now, these are some of the real pictures, the transmission electron micrographs of multi-walled nanotubes, and you can see some of them are broad and wide, and this scale is of 100 nanometers, and so this diameter is, this is a very thick nanotube. These are thin nanotubes. So, this may be of the order of maybe 5 or 10 carbon layers are there in this tube. So, this may be a 10 nanometer or 5 nanometer tube, this may be a 15 nanometer tube, and none of them are single wall nanotubes, because single wall nanotube the diameter will be of the order of 1 nanometer in general. Now, so nanotubes can be straight, they can be spiral, and this they can be of the type of springs. It depends how you grow these nanotubes. Then you can control, then you need to know how to control the shapes of these nanotubes, how to get them straight, how to get them in the spring fashion for certain applications. So, that depends on the growth conditions, how you are doing the discharge, or if you are doing using a laser, how are you creating these nanotubes, are you using a metal catalyst. Many times metal catalysts are used to grow carbon nanotubes. So, all these things matter to ultimately control the shape of these nanotubes. Now, here you can see a transmission electron micrograph of bundles of single walled carbon nanotubes. So, these are single walled nanotubes, but there are many such nanotubes. So, this is one nanotube, second nanotube, this is the third nanotube. Like that, there are several nanotubes which are forming a bundle, right. So, this ability of these nanotubes to come together is through van der Waals forces, and these are again pictures of nanotubes. This is a curved nanotube, and you can see the scale is of 5 nanometers. So, this diameter is of the order of 1 to 1.5 nanometers typically for a single walled nanotube. So, these are all single walled carbon nanotubes. Now, how to roll the nanotube, as we were discussing? If you have one layer of graphite, which is called graphene. So, this is a graphene sheet. So, you have all 6 membered carbons forming the sheet, and how do you roll this sheet? Because if you roll this sheet in one way, you get one kind of nanotube. If you roll it in another way, you get another type of nanotube. So, there are certain definitions. So, in this hexagonal lattice, you define what is called a chiral vector. So, in this 2 dimensional lattice, you define a chiral vector C h, which is dependent on 2 vectors a 1 and a 2. So, these are the 2 vectors a 1 and a 2. So, in any hexagonal lattice, you can define these 2 vectors, and what are the numbers or the coefficients of these 2 vectors. So, if you take a very large a 1 and a very small a 2, that means n is very large and m is very small, you will get one type of rolling. If you take n and m both same, then it will not result in a chiral, it will result in something else. If you take n some number and m you make it 0, then you get another kind of nanotube, again it will not be chiral. So, the chirality of the tube is dependent on this formula, and from this formula you can define the chiral angle theta. And so, these vectors and their coefficients are important, the coefficients are very important, and also what is, how do you end the nanotube toward, if you want to close the nanotube at the end and not leave it open, then what, how do you cap it. So, these are certain things which give flexibility to the various kinds of nanotubes that you can generate using a simple graphene sheet, but just based on the angle or the chiral angle at which you are rotating this planar structure or rolling the planar structure into a cylindrical structure. So, that is what I said, if you take a vector a 1 and a 2 such that the coefficient of a 1 is n and a 2 is 0, that means the vector that you are taking is in this direction, because a 2 is 0 and only a 1 exists. So, you are looking at this vector, and that means this is the n 0 vector. So, this is called the zigzag nanotube. The nanotube that you will get if n has a value and m is 0, then if you roll the graphene sheet in that manner, then you ultimately end up in a nanotube whose direction, this will be the direction of the nanotube, and it is called a zigzag nanotube. So, the coefficient m is 0. However, you can choose any other coefficient n and m. If you choose n equal to m, that means n and m both are same, then your direction will be in this manner, because you have the same magnitude, the coefficient of this vector and coefficient of this vector both are same. So, you will have a resultant like this, and that is what it is being shown. This is parallel to that the resultant which you get here, and you will get the n n carbon nanotube, which is called commonly as the armchair nanotube. So, the zigzag nanotube and the armchair nanotube are two special cases. All other nanotubes, what if you take any other value of n and m, you will get chiral nanotubes, but n 0 and n n, that means the same value for n and m, will give you zigzag and armchair nanotubes. So, this is the n comma n is a naming scheme. It tells you about the vectors which you have chosen. These coefficients tell you about that, and it will tell you about the chirality of the nanotube, which will result if you roll the tube in such a manner that the coefficients which you have chosen are n and m. And this is very important in finding out the property, because the properties of the nanotube will depend on this factor. So, the integers n and m, as I discussed, tell you about the unit vectors along two directions in the planar graphene layer or the carbon layer, and if m equal to 0, the nanotubes are zigzag. If n and m are same, then they are called armchair. Any other value of n and m, they are called chiral nanotubes, and the diameter of an ideal nanotube can be calculated using n, m and a, where a is this value 0.246 nanometer, and actually it comes from this distance. So, it is the distance between this carbon and this carbon, the carbon which are 1 and 3 positions. If you measure this distance, that is equal to 2.46 angstrom or 0.246 nanometers. So, that is the value of a. If you use that value and you know what is n and what is m, you can calculate the diameter of any nanotube. Now, when you look at these nanotubes which result as you roll them in a particular fashion, for example, when m is equal to n, then you get the armchair type of nanotube, and the angle which you have is 30 degrees, the chiral angle. Of course, this here 5 means m is 5 and n is 5, and it gives you a nanotube like that, and at the end if you want to close it, this part will look exactly as half of the C60 molecule. So, if you have an armchair nanotube, the capping part will be C60 molecule. So, exactly like the C60 molecule. However, if you have a zigzag nanotube, a zigzag nanotube has a theta value of 0, and if you come to the end of the nanotube, you cannot close it with a C60 molecule. You have to close it with a C70 molecule, and that is what is shown here. So, if you take half of the C70, that will exactly fit at this part. So, how to cap the end of a nanotube is also dependent on what kind of nanotube it is. If it is an armchair nanotube, only half of C60 can cap it. If it is a zigzag nanotube, then half of a C70 molecule can cap it. If it is any other kind, for example, this is chiral molecule, it is not zigzag, it is not armchair, and the angle theta is neither 0 nor 30, it is in between 0 and 30, then that chiral nanotube will have an end which is neither C60 nor C70, but is a half of C80 molecule. So, a half of C80 molecule will cap it. That means, for different types of nanotubes you need different types of caps. The properties of nanotubes change significantly with the n and m values, and one like electrical conductivity is a very important property, and it shows drastic difference. You can have metallic nanotubes, semiconducting nanotubes, and these properties have been used for applications. One of the first applications was a molecular field effect transistor, and this was made in 2001 by IBM, who showed that if you use these carbon nanotubes, you can make a molecular field effect transistors, which is a great invention, because you are lowering the size of the transistor. From a normal transistor, one molecule is being used as a transistor, and this was done in 2001. So, there are several other applications of these nanotubes. Look at the mechanical properties of these nanotubes. So, carbon nanotube compared to stainless steel, carbon fiber, glass and Kevlar. Kevlar, you know, is a polymer, and it is used in bulletproof vests. If you compare even with Kevlar, most of these numbers you see for carbon nanotube are much higher than these numbers, right. So, look at the strength. The strength is 10 to 60 for carbon nanotube, whereas none of these are of the order of 10, they are all less than 5, whether it is steel, whether it is carbon fiber, or whether it is this polymer which is used for bulletproof vests. So, today we have discussed several of the features of carbon nanotubes and fullerenes, and we will continue our study of carbon based nanostructures in the subsequent lectures. Thank you very much.